Hello my friends and welcome back to the FUTech HD channel. At the heart of Severstal Dearborn is a new, state-of-the-art blast furnace, which operates 24 hours a day, year-round, producing 6,000 tons of molten iron per day. This advanced furnace is the cornerstone of a steelmaking process that includes sophisticated cold rolling and galvanizing facilities. The mill even has its own railway to support the extensive logistics required for its operations. Since many years ago, more than $1.6 billion has been invested in the modernization of the mill, transforming it into one of the most modern and efficient steel-producing locations in North America. In the blast furnace, iron ore, coke, and limestone are conveyed into the top of the furnace while superheated air is blown into the bottom, elevating the temperature to 4,000 degrees Fahrenheit. This creates chemical reactions that form molten iron. Technicians control and manage the operations from a highly automated control pulpit, the mission control, for blast furnace operations. A robotic arm drills out a clay plug, causing a cascade of sparks as the furnace is tapped, and molten iron flows into insulated bottle cars. These cars are then transported via the mill's own railway to the next stage of the process, steelmaking. At this point, the molten iron is not yet steel. The contents of the bottle cars are poured into huge ladles and transported by overhead crane to the basic oxygen furnace, BOF, where steelmaking begins. Before the molten iron is poured into the BOF, a load of scrap metal, a natural byproduct of the area's many automotive processing plants, is added, creating a mix of approximately 25% scrap and 75% molten iron. Pure oxygen is blown into the mixture at more than 21,000 cubic feet per minute, removing carbon, melting the scrap, and creating steel. The molten steel from the BOF is then poured into a ladle capable of carrying 250 tons and brought to the Ladle Metallurgy Facility, LMF, where precision chemistries are produced. Electrodes are lowered into the ladle, reheating the liquid steel while alloying elements are added to achieve the required chemistry. This process controls the chemistry, cleanliness, and temperature of the steel. Depending on the specific requirements, the ladle may be transferred to the neighboring vacuum degassing facility, which can produce ultra-low carbon steels with superior formability and strength. Finally, the ladle is carried to one of the mill's continuous casters. The liquid steel is poured through a refractory shroud into an intermediate vessel called a tundish. As the steel flows downward from the tundish into the caster, water-cooled copper molds reduce its temperature, and the steel begins to solidify into a slab at the bottom of the copper mold. This slab is then further processed to produce high-quality steel products for a variety of applications. The 8-inch thick steel slab undergoes further cooling with a fine water mist, and gas torches cut it to the customer's specified length. Each glowing hot slab is bar-coded before its journey continues to the hot mill. These massive slabs, which can weigh over 63,000 pounds, are heated to more than 2,300 degrees Fahrenheit, making them pliable for rolling and hot reduction. As the slab exits the reheat furnace, it first enters a scale breaker to remove surface scale. It then moves to the roughing mill, where the 8-inch thick slab is reduced to 1.5 inches. The red-hot slab continues to the 7-stand finishing mill and is further reduced to the ordered gauge, as thin as 0.070 inches. A slab initially 33.5 feet long can transform into a coil of steel about 4,100 feet long in just minutes. The ribbon of steel travels over a run-out table, where it is cooled with water sprays programmed to meet the specific physical requirements of each order. With increasing velocity, the red-hot steel arrives at the hot strip mill's down coiler, where it is rolled into huge coils. These coils are then banded and robotically marked for accurate tracking. These hot-rolled bands may leave the plant to be used in manufacturing a wide variety of products or may be further processed downstream into cold-rolled or coated steel products. To produce cold-rolled products, the hot-rolled band is transported to the Pickle Line Tandem Cold Mill, PLTCM, launched in 2011. Severstal Dearborn's PLTCM represents cutting-edge technology, adding precision and quality control to the cold rolling process. Coils are moved into the PLTCM on an automated materials handling system, reducing potential damage and maintaining coil identity. The automated coil preparation station safely removes the bands and optimizes product yield by cutting off only the necessary portions. The coil is then lifted to the PLTCM, where all scale is thoroughly removed from the steel before it continues into the cold rolling process. This meticulous process ensures the production of high-quality steel products, ready for various demanding applications. The 5-stand-6 high mill at Severstal Dearborn, equipped with advanced universal crown technology, enables the production of a wide range of product thicknesses and widths. This precision machinery allows for the creation of products from ultra-low carbon steel to advanced high-strength steel. A strip surface inspection station ensures comprehensive surface inspection under tension without disrupting the processing flow. The exit coil handling system then automatically bands, marks, and applies barcode tags to the finished coils. At this stage, the coil is a fully hard, cold-rolled product. Depending on the order requirements, the coil may need annealing, a process where coils are stacked in a hydrogen atmosphere furnace to soften the steel and restore ductility for additional processing. In the temper mill, the coil is further reduced to meet customer specifications for gauge, surface, and mechanical properties, producing fully processed cold-rolled steel. To meet the growing demand for improved coated products, Severstal Dearborn invested in an exposed hot-dip galvanizing line, HDGL, with advanced high-strength steel capabilities, launched in 2011. The HDGL was designed to optimize the processing of cold-rolled coils from the adjacent PLTCM. After loading the full hard coil onto the line, a high-powered cleaning system creates an extremely clean surface for the highest quality galvanized and galvannealed products. A 5-section, all-radiant tube, computer-controlled furnace heats and then rapidly cools the steel, enhancing its strength across a wider thickness range. The line can produce both galvanized and galvannealed steel using a dual-pot system. The fabrication process for hollow structural sections, HSS, begins with receiving hot-rolled steel or hot band coil at facilities in Birmingham, Chicago, and Trinity by rail or truck, and at Marseille and Decatur by barge. Upon arrival, the coils undergo thorough inspection to ensure they meet the required chemical and mechanical properties. This data is meticulously tracked from the start of the manufacturing process to the finished tube product. Once inspected, the wideband coils are slit to the specific width needed for the outer diameter of the welded mother tube size. Each tube size has a corresponding slit width. These slit coils are then stored for easy and quick access, organized by gauge and heat number. When needed, the slit coils are mounted on the tube mill entry, where they are unwound into an accumulator. This device allows the tube mill to run continuously by welding the head of one coil to the tail end of the previous coil. The forming process begins by gradually shaping the strip into a round form, which is essential whether the final product will be a square, rectangle, or round welded tube. The edges of the tube must be perfectly aligned before entering the welding process. Electric resistance welding is utilized, with the edges heated while rolls apply extreme pressure, forging the edges together and forcing out excess material and impurities. This excess material, known as flash, is removed from the outside of the tube with a carbide cutting tool. Inside flash can also be removed on some sizes and gauges at an additional cost, which is important for applications requiring a smooth interior surface. After welding, the tube is cooled with a water-soluble coolant mixture that aids in the forming process and prevents rust. The next stage is the sizing section, where the welded tube is further worked to ensure consistent dimensions and proper shape, whether round, square, or rectangular. This cold working process enhances the tube's yield strength, tensile strength, and elongation properties as required by ASTM specifications. The final shape is achieved in the last few stands of the tube mill, known as the squaring section, with the Turk's head stand playing a crucial role in straightening and dead-twisting the tube before it is cut to length. The tube mills can cut tubes to lengths specified by customers or to stock lengths of 20, 24, 40, or 48 feet. Custom bundling and lengths as short as 20 feet or as long as 82 feet are also available. The Birmingham and Marseille divisions offer milling saw operations for precise length tolerance with minimal pigtail or large burrs. Quality is a cornerstone of Nucor Tubular products. The inspection process ensures that each tube meets the required specifications. Various tests are conducted, including outer and inner diameter measurements, wall thickness, length, straightness, squareness, twist, crush, tensile, yield, and elongation tests. Additionally, customer-specific testing requirements are fulfilled. The quality management system is based on ISO 9001 to 2015 principles and elements, incorporating best practices from the TS 16949 automotive standard. Finished tubes are tagged with identifying information for traceability, allowing tracking each tube back to its production details and the origin of the steel. For customers needing lengths shorter than 20 feet, all Nucor Tubular Products divisions have in-house band saw cutting capabilities and can miter cut any angle up to 45 degrees for precise, ready-to-use parts. The company produces a wide range of ASTM A500 shapes and rounds, including squares from 1/2 inch square by 16 gauge to 12 inches square by 0.625 inch wall thickness, rectangles from 1.5 inches by 1 inch by 16 gauge to 16 inches by 8 inches by 0.625 inch wall thickness, and rounds from 0.84 inches outer diameter by 0.109 inch wall thickness to 16 inches outer diameter by 0.688 inch wall thickness. The A500 product is made to grade B mechanical properties or grade C for higher strength requirements, with about 90% of the material meeting both grades. The company played a key role in developing ASTM A1085 for enhanced performance in seismic and bridge applications, available in round and square sizes. A 4-week production cycle is provided for large volume jobs, with value-added services such as beveling to enhance productivity. The Decatur and Marseille divisions can bevel pipe at 30 degrees for splicing or plate attachment. ASTM A53 grade B type EERW pipe for low-pressure applications is also manufactured at the Trinity, Alabama division, offering sizes from 2-inch NPS to 8-inch NPS in schedules 40 and 80. Before the introduction of this gantry drill, the fabrication of bridge girders had remained largely unchanged since the transition from riveting to high-strength bolting. Traditional girder fabrication began with the manual layout of hole and stiffener locations. Holes were created by manually positioning magnetic drills and drilling each hole one at a time. After the connection holes were drilled and the connection plates attached, the next girder would be manually positioned relative to the first girder to drill its in-connection holes. One of the main challenges in automating the drilling process for welded bridge girders was that they were often not fabricated precisely as designed due to weld shrinkage and the overall length of the girders. The facility has integrated several unique and innovative machine and software developments to address this issue. Although the production of girder drills was not new, the pull-through design previously required an extensive footprint to accommodate both entry and exit conveyors. Additionally, the varying flange heights along the length of welded girders made them unsuitable for conveying through a traditional drilling line. In contrast, the gantry drilling system processes stationary girders, with the gantry drill traveling the length of the weldment. This design significantly reduces the required system footprint. The gantry system uses laser technology to scan all relative surfaces and end locations once the member is loaded onto the gantry bed. After the probing data is completed, the part program is automatically oriented and adjusted to the actual location and size of the welded member. The gantry drill features direct drive 31 kilowatt spindles that deliver 100% of the motor's power to the tool, generating spindle speeds of up to 5,000 RPM. This spindle design allows for the use of high-performance tools for milling, drilling, tapping, and countersinking. Each spindle is equipped with a 6-position automatic tool changer to accommodate a wide range of tools for typical welded section fabrication. Hole patterns between the flanges and the web often do not share the same length coordinate, but the girder does not need to be positioned to a fixed datum. The gantry drill features a 200 mm sub-axis on each spindle, enabling simultaneous processing of hole patterns, scribing, or milling on all surfaces, even if they are not inline. Holes larger than 50 mm can be milled to the required diameter, and typical web preps can be generated by milling the web and flanges. With proper tooling, radii can be milled easily to complete the end preparation. This sub-axis capability makes the gantry drill well suited for milling operations, with the spindle active in multiple axes while the part and gantry remain rigidly clamped. This is also essential for scribing operations, eliminating the manual layout of attachments such as stiffeners for subsequent welding. Deeper scribing can be generated for part identification, visible even after painting. Rugged HSK-80 tool holders are part of the system to accommodate multiple milling applications, further enhancing the diversity of tasks that can be accomplished for large, heavy, and uniquely shaped parts. The vertical spindle has the innovative capability to articulate to any one of 3 positions, expanding the gantry's ability to process up to 5 surfaces, addressing applications such as end milling. The gantry drill systems are available in various envelope sizes, ranging up to 4 meters in width and 1.8 meters in height. Its expansive capabilities address the processing of large, heavy, and uniquely shaped welded elements that may not conform to traditional conveyor line processing. The structural steel fabrication process has been revolutionized by the advent of sub-axis positioning drills, allowing for unprecedented speed and precision in drilling operations. The ability to produce 60 offset holes in 76 seconds in a 16 inches beam can only be accomplished with a Ficep drill saw featuring sub-spindle positioning. This advanced technology ensures that all spindles are fully productive, generating a typical offset hole pattern in both flanges and the web with maximum efficiency. Enhanced productivity and precision. The drill saw systems, such as the Endeavor and Valiant models, demonstrate the significant advantages of sub-axis positioning drills over traditional fixed spindle drills. Each spindle in these systems is fully independent and capable of positioning along the length of the section. This independence allows for simultaneous scribing on both flanges and the web, a task that fixed spindle drill lines can only perform on one surface at a time. Furthermore, with the underside scribing option, sub-axis positioning enables scribing on 4 surfaces simultaneously, vastly improving productivity. Milling and drilling capabilities. One of the standout features of the Endeavor and Valiant drill saw systems is their ability to mill on 3 surfaces simultaneously, a feat unachievable with traditional milling drills that lack sub-axis positioning. This capability is particularly beneficial when working with structural steel beams, such as the EP 416 wide flange. In a typical operation, the drill can create flange holes with a 20 mm (0.8 inches) diameter and web holes with an 18 mm (0.7 inches) diameter, achieving a total of 60 holes in just 76 seconds. The precision and speed of these operations are essential for maintaining high productivity levels in steel fabrication. Comprehensive CNC drill line systems. Ficep offers the most comprehensive line of CNC structural drilling systems available in the market, catering to a wide range of drilling applications for structural steel. Their product line includes 34 different CNC drill line systems, ensuring that there is a solution for every application. These systems can function as standalone CNC drill lines or in tandem with CNC-controlled saws or robotic coping systems, available with both plasma and oxy-fuel options. Intelligent fabrication. Intelligent fabrication is at the core of the CNC drill line systems. This approach allows fabricators to simulate jobs or production sequences in conjunction with erection needs, optimizing the fabrication process. Once the optimal sequence is determined, the material is loaded and scanned onto the material handling system, initiating the fabrication process. The WIN handling software optimizes handling steps and process selection, completing the fabrication operation efficiently without the need for direct operator intervention. As material moves through the system, routing and corresponding CNC programs for operations such as shot blasting, sawing, drilling, thermal cutting, and layout occur automatically. This automation ensures that all material handling functions and CNC operations transpire simultaneously, maximizing system efficiency. By eliminating decision-making delays through intelligent fabrication, Ficep ensures that maximum system efficiency is always achieved within the smallest possible footprint. The Salvagnini P2 panel bender is a highly versatile sheet metal processing center designed to produce a wide range of items. This makes it an excellent tool for businesses, including those that may not have previously considered a panel bender as their ideal bending machine. The P2 utilizes universal bending tools that automatically adapt in cycle to the panel geometry, eliminating the need for machine downtimes or manual retooling. This feature supports batch 1 or kit productions, significantly enhancing efficiency. The P2 incorporates advanced technical solutions, such as direct drive and pneumatic and electric actuators, which ensure that the machine is both environmentally friendly and safe for operators, without compromising productivity. It operates with a minimal quantity of long-life oil within a fully sealed circuit, highlighting its commitment to sustainability. Integrated adaptive technologies like advanced sensors, bending formulas, and MAC 3.0 make the P2 system intelligent and capable of automatically adapting to changes in material and external conditions. This reduces waste, eliminates the need for corrections, and broadens the range of producible items. Additionally, proprietary software solutions such as Links, Stream, and Ops facilitate seamless communication between the P2 system and the various company departments involved in the production flow, ensuring smooth and coordinated operations. The P2 also offers customizable solutions to cater to specific needs, including auxiliary tools and additional devices for special geometries. It supports different loading and unloading solutions, with options for additional doors, PIN 2, or robots, PIN 3, enhancing its flexibility and adaptability to various production requirements. The Multi-Mover M700 is a cutting-edge mobile transport solution tailored for the rigorous demands of steel mills, specifically designed for handling extremely heavy loads. This vehicle is packed with advanced features that prioritize safety, efficiency, and versatility, making it an indispensable tool in the modern steel manufacturing process. One of the standout features of the Multi-Mover M700 is its remote control system, which allows operators to manage the vehicle from a safe distance. This feature is particularly crucial in the hazardous environments of steel mills, where the handling of molten metal and other heavy materials can pose significant risks. The remote control capability not only enhances operator safety by keeping them away from dangerous areas but also ensures precise maneuvering of the vehicle, reducing the risk of accidents and improving overall operational efficiency. The Multi-Mover M700 is engineered to handle an impressive maximum payload of 700 tons. This capacity makes it suitable for transporting vast quantities of hot metal or other heavy materials within the steel mill. The ability to move such large loads in a single trip significantly boosts productivity and reduces the number of transport cycles required, leading to more efficient operations and lower operational costs. A key application of the Multi-Mover M700 is the transport of hot metal to pig casting machines. Complementing the capabilities of the Multi-Mover M700, the Multi-Mover Y550 is another advanced transport solution designed for specific tasks within steel mills. This vehicle focuses on mobility and safety, making it an essential asset for transporting hot metal to various locations within the production facility. Hot metal transport to deposit area. The primary function of the Multi-Mover Y550 is the transport of hot metal to designated deposit areas. This task is critical in managing the flow of molten metal within the steel production process, ensuring that it is efficiently directed to the appropriate locations for further handling or processing. By optimizing this transport task, the Multi-Mover Y550 helps streamline operations and maintain the smooth flow of production. With a maximum payload capacity of 120 tons, the Multi-Mover Y550 is well suited for carrying substantial loads of hot metal. Despite its slightly lower capacity compared to the Multi-Mover M700, the Y550's design ensures it can handle the rigorous demands of steel mill operations effectively. Its robust construction and engineering guarantee reliable performance under heavy-duty conditions, making it a versatile tool for various transport tasks within the mill. The Slag Taurus P120 is a state-of-the-art transport vehicle designed for handling slag in steel mills with exceptional efficiency and safety. With a maximum payload capacity of 120 tons, it is built to carry substantial loads, making it ideal for heavy-duty operations. One of the key features of the Slag Taurus P120 is its excellent maneuverability. It is engineered to navigate the often tight and complex environments of steel mills with ease, ensuring that it can reach slag deposit areas quickly and efficiently. This agility reduces transport times and enhances overall operational efficiency. The vehicle is equipped with a protected support system that safeguards its critical components from the harsh conditions typical of steel mill operations. This system minimizes wear and tear, thereby extending the vehicle's lifespan and reducing maintenance costs. The Slag Taurus P120 also features a sophisticated dumping system with overload protection. This ensures that slag is safely and efficiently unloaded without risking damage to the vehicle or compromising safety. The overload protection system prevents the vehicle from exceeding its operational limits, enhancing reliability and operator safety. The manufacturing process of a slag pot begins with sand molding to shape the slag pot. Sand molding provides the flexibility and accuracy needed to form the intricate details of the slag pot, ensuring a solid and reliable structure. Trunnions, which are essential for handling and rotating the slag pot, are cast in if required. These trunnions are typically manufactured from steel material S355 J2G3, providing the necessary strength and durability for heavy-duty use. Melting is performed in an oxygen steel plant. The ladle used has a capacity that supports a continuous bottom pouring process, with the pouring speed meticulously controlled to ensure uniformity and quality. Metal analysis is conducted using a computer-linked spectrograph to ensure the composition meets the stringent requirements, providing a reliable and high-quality metal for the slag pot. The heat treatment process is crucial for achieving the desired mechanical properties. The slag pot is heated to a temperature above AR3, followed by austenitizing at approximately 915 degrees Celsius. Controlled cooling in the furnace ensures proper structure formation. An intermediate holding phase occurs at 600 degrees Celsius to 630 degrees Celsius, with cooling completed in the furnace down to 300 degrees Celsius. This precise temperature control ensures the slag pot's durability and performance under extreme conditions. Finally, the inner surface of the slag pot is processed to remove any surface discontinuities that might cause slag sticking, ensuring a smooth and functional surface. The castings are descaled by shot blasting, and the outer surface is coated for protection during transportation. This filling and dressing process ensures the slag pot is ready for use in steel manufacturing and other industries, providing a high-quality and reliable component. The automatic H-beam production line is a highly efficient and technologically advanced system designed for the fabrication of H-shaped steel structures. By integrating various automated processes, this production line significantly reduces the need for manual intervention and the frequent use of traveling cranes. The primary aim is to streamline the production process, enhance productivity, and ensure precision in manufacturing. The process begins with the cutting layoff, where steel plates are cut into desired lengths and shapes. Precision cutting is crucial to ensure that the subsequent assembly and welding processes are accurate. After cutting, the steel plates are assembled into T-beam configurations. This step involves precise alignment and fitting to ensure structural integrity. Once the T-beams are assembled, they undergo a 180 degrees hydraulic overturning to ensure they are correctly positioned for the next stages of assembly and welding. The T-beams are then further assembled into H-beams by fitting additional steel plates to form the characteristic H shape, ensuring all parts are securely positioned. Following this, the H-beam undergoes a 90 degrees hydraulic overturning to reposition it for efficient welding. The automated system then shifts and feeds the beams through the production line using conveyor rollers. This automation minimizes manual handling and accelerates the process. The first welding scene is executed with high precision using automated welding systems that ensure consistent and strong welds. The H-beam is then turned 60 degrees using chain overturning mechanisms, preparing it for the next welding scene. This process is repeated for multiple welding stages, each followed by specific overturning and shifting operations to ensure comprehensive welding coverage. After all welding seams are completed, the H-beams often require straightening to correct any distortions caused during the welding process. This involves straightening the plates after a 180 degrees hydraulic turn and return, ensuring the final product meets quality standards. The automation in the H-beam production line offers numerous advantages. Increased efficiency is achieved as automated systems reduce production time and labor costs. Enhanced precision is ensured through consistent and accurate operations, resulting in high-quality output. Safety is significantly improved by reducing manual handling and crane usage, minimizing the risk of accidents. Additionally, the streamlined processes and reduced downtime lead to substantial cost savings, making the system cost-effective. The TruBend Series 5000 is a renowned bending machine celebrated for its exceptional production productivity. This efficiency stems from a host of innovative features that streamline every phase of the bending process, from programming and setup to the actual bending operation. Central to its performance is the on-demand servo drive, which operates quickly, quietly, and with remarkable energy efficiency. This drive mechanism ensures operations at a high speed of 8.5 inches per second, significantly boosting productivity while minimizing noise and energy consumption. The machine is equipped with advanced angle measuring systems from the automatically controlled bending (ACB) family, ensuring precise angles from the first part onward. The ACB wireless and ACB laser systems simplify and expedite the measurement of bending angles. Furthermore, the ACB speed system optimizes the process by measuring springback only on the first part and applying the corrections to subsequent parts, reducing cycle time by up to 35%. This intelligent angle measurement is complemented by the ACB Smart software, which includes a continually updated materials database, allowing operators to select the best settings for each job directly from the control panel. One of the standout features of the machine is its lower tool displacement capability, which enables special applications such as folding. This feature, combined with the machine's 6-axis back gauge, provides complete production freedom, allowing the machine to handle complex bending operations with high precision and flexibility. This adaptability makes the TruBend Series 5000 suitable for a wide range of bending tasks, enhancing its value in various production environments. The user-friendly design of the machine is another significant advantage. The machine is controlled via the touchpoint TruBend system, which offers an intuitive interface akin to using a tablet PC. This ease of use simplifies the programming and operation processes, making the machine accessible even to operators with minimal training. The Toolmaster automatic tool changer further enhances productivity by automating all tool setup operations, ensuring that the machine is always ready for the next job without manual intervention. Ergonomics and operator comfort are also key considerations in the design of the TruBend Series 5000. The machine incorporates numerous ergonomic features to enhance safety and ease of use. Additional LEDs provide perfect illumination of the work area without generating heat, ensuring a comfortable working environment. These design elements not only improve operator satisfaction but also contribute to safer and more efficient operations.